That's a really nice and generous interview to both talks. But indeed, I'll talk about computer vision first. And as intimated, I built a private research lab, primarily around computer vision, at a company, Indeed, which is a subsidiary of Milestone. Canon. I'm not an academic anymore, though I have lots of university collaboration. But I am a frequent speaker at summer schools. I was going to say this is my 10th anniversary, but then you just reminded me about Oxford. So it turns out it's 12th. So thank you for having me along. I will do my best to have a good 12th anniversary. I'd like to talk about history a little bit, and ethics especially, because the company that I work for is in security and surveillance, and perhaps you might have some qualms about what that means in the modern world. So let me take you back and then give you my point of view of how ethics has developed in AI. I think yesterday Isabel, Professor Augenstein, mentioned the earliest date when we thought about AI. Anyone remember where Isabel pitched that? Nobody's brave this morning. I'm going to be more specific with my questions then to get some interaction. But I'm going to contradict a little bit and say the first time that we, humanity, started to think about these topics was when Ada, Countess of Lovelace, worked with Charles Babbage on physical computing, okay? And Ada was a skeptic. She said this analytical engine that they built only does what they tell it to. And in very many senses, she was the first computer programmer. But she said only when computers originate things should they be believed to have minds. And she said everything that we have done with the computer, there is no origination. There's just following an algorithm that it's given. So she was a skeptic whether this would happen. And she lived in a time when we were really thinking about this. This was sort of a relative of hers, Mary Shelley, wrote the book Frankenstein, and really said, what is the effect of science and industry on what it means to be human? Mary Shelley thought, yeah, you can reanimate bits of corpses glued together and you will have something that thinks, and does it really think like a person? There's Ada working on, working on this thing with Babbage and saying, is it perceivable that this thing could lead to some sort of mind? But what she was working on, this is Ada's translation of a paper about the computation of Bernoulli numbers. And her contribution, this animation that's the black bit. Her contribution is in this footnote, note G, where she said, we can do this on this physical computer, and here's how we have to configure it, here's how we have to program it to follow this algorithm to compute these numbers. Now, if you jump ahead 100 years, then you have Alan Turing. And Alan Turing, very famously, was thinking about AI, and he said the same question, can machines think? And you might well know that one of the tests that we work towards, certainly in the 20th century, we called the Turing test. Can a would-be AI have a conversation with someone such that that person doesn't know that they're talking to a machine? And what Alan did was referred back to Ada Lovelace. He said, Lady Lovelace's objection is one of 6 objections that I consider to the idea that this might happen. Okay, so if we look at the history of Turing, before the war, he was working very much on maths at Cambridge. So in that's not as big as I thought. In 36 before the war, he was working on this mathematical problem set by David Hilbert at the turn of the century. So in 1900, Hilbert introduces these problems to be worked on during the 20th century. A third of the way through, then you have people like Gödel and Church and Turing looking at this one particular problem, the Entscheidungsproblem. And he introduces this idea, computation can be reduced to the relationship between numbers. And if a machine can derive one number from another, that is computation. In fact, it's all of computation. We've never gone beyond this thing. The machine that he envisaged was a completely theoretical construct that we called a Turing machine. But then the war happened, and Turing started working on physical computing. Okay, so after the war, he publishes this paper on computing machinery and intelligence. And I take this stretch of conversation out because where we are today, as we're sitting and standing here, this is the kind of conversations that we're talking about, that Isabel was showing. So let me cherry pick some of them. Add two numbers together. It's ironic because we were saying language models are actually not that great at that until you go agentic and say arithmetic was solved, as we said yesterday, very many decades ago with a calculator. You just need to put the two things together. You need the AI that's good at conversation using a language model and the computer that's very good at doing arithmetic. Okay, here's another one. Do you play chess? Yes, I do. Okay, here's a description of the board after I've made my move. Now it's your move. And Turing said, yeah, well, what would happen is there's a bit of a pause while you work out what your move is, and then you give an answer. So if we were in that imitation game setting where you write a letter or a card, someone takes it through to the other room, and then they bring a card back, this is what Turing said would be intelligence-like. If you can do some maths, if you can play chess, and then the counterexample almost is, if you write on a card, write me a sonnet about the Forth Bridge, this bridge in Scotland, then it would be perfectly human or indistinguishable from a general human for the card to come back, I don't write poetry, I'm not going to do that. Okay? So he wasn't talking about omniscience, he was talking about, is this human-like? And some things humans say, I don't know how to do that. Okay? So, Ada, Alan, I want to talk about this person. He might be less known, though he deserves to be known a little bit. This is Woody Bledsoe, and he took things a little bit further and said, I don't just want a computer to have a mind. This was him retrospective on his career in 1985. He said, in 1960, I was thinking, what does it mean for a computer to have eyes and ears and to be able to articulate itself with arms and legs? So what was he working on? One of the first things, and this was still in the 50s, at the end of the 50s, he wanted to talk about reading by machine, okay? And he's talking about real hardware, in a sense. So he says if we have this matrix of optical parts and they respond to light and to dark, can we recognize letters from that? Okay? And in fact, what he was really doing was punching these into punch cards, given the computing that he had available to him at the time. And then his approach was to pick pairs of essentially pixels, okay, and to work out how good a predictor they are of a letter. And you might know from neural networks, very similar thing. We start by randomizing. And actually, in this search space, he said 75 pairs, whereas 150 choose 2 is a 2 orders of magnitude bigger search space. Okay, so he's not going to do it exhaustively, look at all the ways to combine these pixels. Instead, you randomize, and you pick 75 of these pairs, and then use an approach called hill climbing. Raise your hand if you've heard of hill climbing. Awesome. Raise your hand if you've heard of gradient descent. About half for hill climbing, almost everybody for gradient descent. They're very similar things, okay? It's just upside down. Hill climbing that we worked on first, you're trying to get to a maximum. You're trying to optimize to a maximum, but what you really do is often optimize towards a local maximum, whereas gradient descent, you're going down. It's actually more subtle, the difference between that. He is talking about a finite search space. Everything is discrete. You've got these pixels, you've got 150 pixels, he started in numbers, so you've got 10 classes okay? And there are all of the combinations that you could make of pixels to predict those numbers. That's finite. And in hill climbing, you try to get towards the better combination, which leads you to this maximum in terms of the right class that you're predicting. But very close. Gradient descent actually says you don't just look one step here and one step there because there are no steps. It says if there's a derivative to the function, then you're maximizing the derivative. So, it gets into the 60s, and he starts to talk about this thing, facial recognition. He says, he defines this problem as in, if you give pictures, and originally he took 10 people, this was his starting point, and give the pictures to a machine, show them those examples, and then give a novel picture, an unseen picture, can it recognize which of those 10 individuals that was? Okay? Now, Bledsoe was a big believer in something that he called man-machine. Today, we would probably say human-in-the-loop computation. So he'd worked on essentially maths, they're improving. He'd worked on what now we would call optical character recognition, and now he's working on facial recognition. And he says the human in the loop might be able to help out with a lot of work here, that the human, when the picture is presented, could specify what the sex of the person is, or they could specify what the race is. And now that, I'm admitting I work in the surveillance industry, facial recognition is already a touchy subject. This subject of sex and race, now we're starting to talk about those things against which systems can be biased. Okay? Bledsoe went a step further and said, okay, I've changed my mind. Actually, the computer can recognize someone's sex, or the computer can recognize, and he doesn't just say race, he uses this very dated term of Oriental people from the norm, which is white. So, let me go back to that quote that he made about what he wants. Okay, eyes and ears, arms and legs. The full quote, or that full sentence was, I did not dream of a worthy cause, such as helping the poor and handicapped. My dream was just the excitement of seeing, can we get the machine to appear to act like a human? Okay? So I sort of like Bledsoe, but I sort of don't like him either. In the 80s, this is a really interesting artifact, I think. So, 87, Bledsoe gets a letter from this chap called Starkey, who works at the West Midlands Police back in England, where I'm from. He's a chief inspector, and he says, Professor Bledsoe, the chief constable, so the highest-ranking police officer that I work with, is going to allow me to do a part-time PhD. And again, I'm giving sort of a forward reference to different things that you can do in a research career on Thursday. But he said, yeah, I'm allowed to do a part-time PhD on face recognition, essentially. And I'm going to be supervised at Imperial by Igor Alexander. And he is working on perceptrons. Hands up if you've heard of perceptrons. Yeah, half. Hands up if you've heard of neural networks. Same thing. The perceptron is the basis of neural networks, but we don't always use that term anymore. And Alexander at Imperial was working on quasi-parallel methods for training perceptrons. That should sound very familiar, okay? That's the advance that we made in terms of training neural networks. We used a GPU, so it's very parallel. Okay, so he writes this, and why does he want to do this, being in the police force? He wants to recognize criminals, for instance, in banks. And sort of fair enough, People go and rob a bank. People go and defraud. People steal other people's card or the bank's money. Fair enough, I'm happy with facial recognition being used to help those criminals. But he says one more thing that, again, puts me on edge. We could use it in riots. Okay? Now, while a bank is a private space and you have a particular incident that you're investigating, this is the suggestion of mass surveillance, okay? Of, you haven't done anything criminal, but we're going to track you around the world with mass surveillance. If you jump forward to this century, you have, again, the British Home Office. So in 22, we have this commissioner on biometrics and surveillance cameras. In fact, there are two commissioners. There's one for biometric information, and there's one for surveillance cameras. Part of the reason that Britain would have two commissioners is, I'm not sure if this is clear, in the entire world, Britain is number 2 in terms of the number of CCTV cameras relative to the population. Number 2. Who's number 1? China. So, this letter from the Home Office in the UK expresses some concerns about a company called Hikvision. Okay? An anecdote, Professor Augenstein and I were in Tallinn before we came down here. We went to see the Academy of Sciences, couldn't get in, there's a closed gate, and there's a Hikvision camera looking at the gate. Yeah, maybe when we go back to Tallinn you can help us. But that wasn't so much the point. There is a Hikvision camera looking at the Academy of Sciences here. And believe me, there are still quite a few of these cameras, even though the UK, America, Denmark have all said we need to get rid of these cameras. Why do we need to get rid of them? Because of involvement with the Chinese state's human rights abuses in Xinjiang, in case that's not clear, against the Uyghur people. These are the Muslim minority population in Western China. And this is chilling at the end. This persecution is known to rely heavily on surveillance technology, including facial recognition software designed to detect racial characteristics. So what Woody Bledsoe said, yeah, this is great, let's work on facial recognition. Yeah, this is great, we can automatically classify people by race. In the real world, no, this is a horrible thing to do, okay? So again, working for a surveillance company, we say no mass surveillance with our software. We say no racial profiling with our software. We cut you off, you're breaking your license if you do these things, but they are out there. Okay, my last bit of politicking, obviously. So, I want to talk about marginalized groups. Ada was a woman. She was born early in the 19th century. The work that she did was anonymous. Literally, it just says Note G is the first computer programmer, and it doesn't say Ada's name anywhere. She was a countess, a little bit privileged, but that privilege only meant that her job in life was to provide children for the count to whom she was married. She gave him 3 children, and she died at 36. Alan Turing was a gay man born in England early in the 20th century. His work at Bletchley Park, which you may know about the code breaking during World War II, it was hidden under the Official Secrets Act long after he died. It's only on his would-have-been 100th birthday that the British government decided, okay, now we release these documents and we can really see what Turing worked on. What they did much sooner was prosecuted him for being gay. Excuse me? And he killed himself. Marginalized people. Woody wasn't wholly privileged. He came from a farming family in Oklahoma. But despite that beginning, he was given a full fellowship at Berkeley, and then he was passed money by the NSA and the CIA. The last time I gave these slides, I gave them to the attachés from all from all 27 EU member states. So Denmark took the presidency last month. They came along to see what's happening in Denmark, and I said, yeah. Here's what it is. I have worked, the reason I left the UK was to keep working with European funding. I'll tell you on Thursday, I've had a lot of it. But I've always had to go to Brussels or sometimes to Luxembourg with my hands held out for some money. Woody? No, they just kept giving him money, and that's why I showed these people at the EU this quote. I didn't even have to ask. I didn't even have to go to Washington. And just to finish the story, he became a patriarch and then a bishop of the Mormon Church and died at a much riper age, at 73. I don't mean to make light of it. He died from degenerative Lou Gehrig's disease. Not a nice way to go, but he had a full life, and he was funded and acknowledged the whole time. Okay, enough politics, enough ethics, some technology. Who recognizes the MNIST dataset? And you probably know why it's been so great for neural nets, because there are hundreds of thousands of examples of handwritten numbers. Anyone know where it came from? Almost. Not postal. It was the census service in the US. So, like the postman, they go door to door, but they say how many people are living here, they write it down, they take those numbers back, they put them on, they transcribe them, they put them onto punch cards, and the first US census was run on a mainframe with punch cards. In any case, 10-class problem, handwritten numbers, gold standard annotation, because this was the US Census. I want to test you out on a few things, and 10 classes is a little bit too much, so I'll talk about a 2-class problem. Okay, you recognize this, right? Dog or muffin. I'm going to treat this as a dog spotting, a dog detection problem, okay, as a very simple case of what we do in applied computer vision. So, to check the terminology, if I say that that is a dog, and we have this language of positive, negative, true, and false, what case is that? Thank you. I think we need to ban you from answering, though. If we say that's not a dog, what's the term for that? Thank you. If we say that that is a dog, and this is a dog detector. False positive. I had some false negative over there. That's the false negative. We're doing dog detection. This says it's not a dog, okay? So it's a false negative. These things matter in terms of statistics and writing papers, but they matter a lot in the real world. I'm going to talk about a very simple example and then maybe some more advanced ones. Okay, let me test you some more. You can make a confusion matrix. You can do all of the labeling, and you can fill that out. And then you can compute this measure. What's that called? Who said which positive rate? It's actually the ratio, remember? So this is when dog is predicted, and we're saying how many times was that prediction of dog correct relative to that whole column. What about this one? I heard that. That's recall. That one's precision. You're an instructor as well. Man, the rest of you have to step up to your instructors. Here's your chance. We can compute this, given the true negative and true positive and the absolute size of the data set. What do we call that? Who said F1? Ah, it's not. That's the accuracy. But you're sort of giving the game away. If you take the geometric mean of those things, what's that called? Yeah, now you've got it. Okay. Let's have a bigger class. When I used to teach summer schools in my youth, I was told by the students more than 1 year that I looked like this guy. Who's the other guy? You're all so young. Instructors, thank you. That is Hugh Grant. As I grew up, and again, I made these slides for EU political folks. So when I was older, I got compared to this guy. I won't ask you. He is a chap called Ed Miliband. He was almost the Prime Minister of England. He's very well known in the EU. He didn't get to be Prime Minister of England because he looks weird eating a bacon sandwich. I am not lying. The tabloid press in Britain said, look at this guy, he can't even eat a bacon sandwich, how could he be Prime Minister? Okay, so just as we had the confusion matrix for a 2-class problem, we can have the confusion matrix for a 3-class problem, but if we're talking about face recognition, the pictures that we present aren't necessarily going to be faces, okay? If I take a camera up there, I actually have to detect all of the faces and then do the recognition on them. So what if, and you can compute precision and recall on that 3-class matrix, but actually I could give it a picture of this is the door to Downing Street where the British Prime Minister lives, and that's a bacon sandwich. Okay? If I really want to talk about those measures, I should talk about 4 classes. I should talk about the fact that some of those pictures aren't going to be people at all. Then I'm going to extend it by 1 more and make it a 5-class matrix. In that submatrix, there's me and Ed. And if we're mistaken for one another, that's a false labeling. So far, so good? Okay. And then 2 new cells. That is my colleague Pam at Milestone. And this is a researcher called Joy Bulamwene. Okay? And if you look at that submatrix, how likely is it that Ed and I get confused versus how likely is it that they get confused, that Pam is labeled as Joy or Joy is labeled as Pam? The bias in facial recognition as we did it means that they are way, way more likely to be confused with one another than we are. And that's a kind of bias. There's something even worse. That square, where it's really Joy, but no person is recognized at all, that's what Joy found when she was a grad student at MIT. She worked with an off-the-shelf face recognition model. She wanted to do this really nice virtual shopping thing with a fake mirror, and more times than not, the facial recognition wouldn't even find her face. Okay? Then she got a white mask and put it beside her in the webcam, and it recognized the mask as a face and not her face as a face. Okay? Now, we sort of said we're not doing a lot of book recommendations, but I am. Please go and read Joy's book. There's a lot. And it takes a lot for me to say it because she's very critical of my industry, but she's very good at being critical. Yesterday we talked about synthetic data. Now I'm going to contradict a woman. Because Isabel talked about a kind of synthetic data, which is using a generative model to produce training data for another generative model, and we talked a little bit about model collapse, which can be the consequence of that. In computer vision, traditionally we meant something very much simpler than that by synthetic data. We meant we've got too little training data, so we just do some algorithmic manipulations. We do flips, we do skews, we do adding noise, we do pixelation, and it just increases a little bit on the data that you have. What I did quite a lot, because part of the problem with facial recognition is if your skin tone matches the background, then it's a little bit difficult to make the distinction. So people with darker skin and dark backgrounds, we want as much training data as we can to make sure that's working robustly. So one thing that I do is semi-synthetic. I really take the face, but I put lots of different backgrounds around it and do the training to try and make it more robust to that contrast. Then there's this thing that we talked about. It exists in computer vision as well. Go to a generative model and say, please give me some faces of black women. Okay, that's not good. That is a bad way to do synthetic data for all of the sort of reasons that we were talking about with model collapse. Also, that what's being generated is generated according to stereotypes. I don't want to recognize young black women based on the pictures of young black women online. Bad idea, a horrible kind of bias. Are you scowling because you're thinking what I'm thinking? If you look at the proportion of different classes of websites that represent young black women, there is a high proportion of one which is not something that you want to train on and represent the stereotypes of people by. Equally, Asian women. Yes, let's get back to some history. I'm a symbolic AI person by training. What do I mean by symbolic AI? Well, in 1945, after the war, we started to have digital computers, and we started to build things like Isabel mentioned Eliza, sort of very first chatbot. It couldn't pass the Turing test according to our definition, but on the other hand, people got really attached to Eliza, so that when Weizmann said, I'm going to close this down, I'm done with my experiment, people said, please don't take away my psychiatrist, I need it, okay? And you see that in recent years as well. Please don't take away my replica model, I need it, okay? So it is sort of persuading some people that it's conversational. One much closer to my heart, because it's where I started to work in computer science at all, which is mathematical proof. The four-color problem was the first time in human history that it's not just a human mathematician. There is a proof assistant, which was AI, proving a new theorem for the first time. Really exciting stuff. I think that's the most exciting thing going on now, right? We're talking about NLP, we're talking about computer vision. Yeah, fine, good, excellent stuff. But proofs in real higher mathematics, not just the arithmetic that Turing was talking about, but in pure math, I want DeepMind to spend all of their money on this problem. Last one, this was the pinnacle of symbolic AI. As I was an undergrad, then Big Blue beat Kasparov at chess. So again, Turing had talked about conversations, he talked about maths, and he talked about chess. We all believed that chess was the mark of humanity, okay? So everything's kind of happened, right? Before the end of the 20th century, we've done all of those things that Turing said. So what's going on with Bledsoe? Sorry, slide order, great. I'll tell you about Bledsoe in order to tell you about machine learning. He was doing feature-based machine learning, okay? He literally said, and you can see it up here, yes, the age, the sex, etc., but then he was saying there are features like interpupillary distance, okay? The distance between the center of your eyes, the length of your nose, yada, yada, yada. You can take a photo and reduce it to these features and learn based on those features. And just an interesting aside, literally use this thing called the RAND tablet, also called the Graphicon, where you could use a stylus to mark these things on a face to measure them. Obviously, that's not the real display. It was this horrible black and green thing, but that's a picture from Bledsoe's paper. If you look at how things advanced there was sort of, in the 70s, there was a schism between feature-based facial recognition people who were saying, yeah, we need these discrete features, and we optimize on classification based on them, and maybe we can do some clever things like edge detection and centroid detection to find and measure those features, but it's all about the features, versus the holistic people that said, no, you take the whole photograph and you manipulate it down to its essence. So you use things like PCA, principal component analysis. This is something called eigenfaces to look for spectral methods-based manipulation of the picture. The left-hand side here, this feature-based machine learning, is kind of the basis of the state of the art when I was an undergrad, okay, and entered research. So people, Isabel mentioned logistic regression. You can do that if you have these measured features. The first gig that I had in research was in NLP, actually, but we were using support vector machines. Again, you've got these features, you represent all of your features in high-dimensional space, and you learn to warp that space so your classification boundaries work, okay? These two things come together and go away with neural networks. When I was an undergrad, I was taught about neural networks, but I was taught they're just not tractable. We can't actually do this, even though they're powerful. But one thing that we found was you have multiple layers, you give it either the pixels or actually used convolutions around those, and what it's learning inside, in a hidden layer, is some kind of features. You haven't chosen the features, you've just presented all of these lengths of pixels, and the thing is learning the features on the whole thing. So these two things come together, and the work goes away. It's just, if we can get the neural network to do this at scale, we just throw it in together with the classification, and it learns to do it. So, history-wise, I don't know, I guess we're out of battery. That came almost first. In '43, these guys, Pitts and McCulloch, came up with this idea of perceptron. Now, there was a bit of an argument with Minsky over what they could do, and the solution is multiple layers. Go away, Minsky, everything that you say they can't do, actually they can. Frank Rosenblatt did something very like Bledsoe. He said, let's have an artificial retina. Let's have photodiodes in a grid and see what the neural network can be trained to do. And he trained it to distinguish circles from triangles from squares. Okay? Start of connectionist, of neural network-based computer vision. It's also Rosenblatt who transformed from this very analog computing, maybe photoresistor, and analog computing to digital, and said this training that we do, these weights that connect the neurons, the perceptrons together, we can compute digitally. You have all of that work around convolutional neural nets with data sets like MNIST. It all looks really, possible on paper, but maybe not something that we could apply at scale until Andrew Ng and his students say, well, that parallelization that we've been talking about for a while, if you take the gaming graphics card out of the machine, it's been made to do all of these, I'm not a gamer, so forgive me if I'm getting this wrong, these polygon manipulations that make the mesh for a 3D object in a video game. The way that it computes those in parallel is basically just linear algebra parallelized, and that's what we need in order to do both the feed-forward inference and the backpropagation. These are both just big bits of linear algebra that you can parallelize. And then, sort of a landmark that surpasses all symbolic AI, okay? In chess, there is a definite scoring to every move, and there is a look ahead that makes sense. Where does this put me in 5 moves in terms of the score that I make by taking others' pieces? In Go, absolutely not. There is no objective measure of how you're doing until the very last move, and the search space is more than the atoms in the universe. So you need a heuristic approach to playing it, and DeepMind did that so well, they beat a world grandmaster at Go. What else was happening? DeepMind started talking about reinforcement learning and said, let's not tell these game players anything at all. Let's just give them this breakout game. Do people know this game? Raise your hand if you've seen Breakout. Keep your hand raised if you've seen these sets of training. A little bit of training, it can't play at all. 2 hours of training, it can play. 4 hours of training, and it's even worked out this strategy, like if you get the ball up there, you get loads of score before you even have to interact with it anymore, from nothing, from just the pixels of that game and the move right and move left, and the score as what you base the reinforcement on. So here's your score, here's a set of pixels, and here are your 2 controls, and that's what it could learn. Fantastic. Everybody was really excited about that until they got excited about this. Remember, Turing said, write me a sonnet about the 4th bridge, and he thought the best thing to do is to say, I don't write poetry. GPT has a go, and it actually writes a sonnet about that bridge. So, of course, everybody's been talking about that for a while. I did, indeed, take a creative writing degree, finished it last year. Midway through that degree, this news came out. People prefer poetry written by large language models. We went to a comedy gig, and they were interacting with the front row, which here is empty, but I insist that we sit on the front row, and they do audience interaction, and they're asking, what do people do? And the people sitting behind us were from Novo Nordisk, because we live in Copenhagen, and everyone they asked is like, got a PhD, got a PhD, got a PhD. So they came to us on the front row and said to me, what do you have? It's a PhD in computer science. Okay, but I'm also studying creative writing. And the comedian said, what a stupid move. Computing is doing everything and everything that people care about. You're learning to write things when what you've just done is create something that can write apparently even better than humans. I don't believe that that's right, but it's fun. It's a nice thing for a comedian to say. How long have we been talking? 40 minutes, I believe. So I think we're 45 minutes through, given the introduction. So instead of going on to applications, I'm just going to give a minute for questions, and then we'll have some more questions at the end. Anybody got some questions about what I've been saying so far? You don't have to. I've got loads more that I could say. Please. Very good question. Essentially, can we classify unseen text and ask, was it written by a human or not? I am bound to say, no, not in general. And I'm also bound to extend that question to say, can we tell if an image was generated, or even more so in my industry, can we see whether a video was generated? Not reliably. You can train adversarial approaches both ways. You can use adversarial training to defeat this recognition and to try and detect it. It's an arms race. And yes, I was a student until September. I will be a student again because I want another master's degree in September. I have what you probably have all had, Turnitin, or an equivalent solution that tries to look for plagiarism. The best thing, or that traditionally tried to look for plagiarism, the best thing that it can do is to look on the web. The thing that it's terrible at is working out, did you write part of this with ChatGPT? People try to do it, and every time they try to do it, it's just easy to find a way to defy it. The best you can say, it's an arms race. And incidentally, those things that you look for in text, they are by far not as good as you can look in the computer vision space. This GPT uses M-dashes. Well, I just did a creative writing degree and wrote a novel. Novelists love to use M-dashes. So please don't look at my text and say it was written by ChatGPT. I spent a lot of time developing that skill and incidentally started using lots of M-dashes. It's a really good question, though. I like it. Any more questions? Then I've had my water, and I'll carry on. So, in 2018, the sort of computer vision that CNNs had already done really well at, which is object detection in the sense of finding objects within bounding boxes and classifying them, well known. We'd been doing that with deep learning with CNNs for a while, but what you should know about industry is adoption is way behind where the state of the art in academic literature is. So literally, I get into this company, and in 2018, they're like, we can do this. We've been trying to do it with traditional computer vision for a long time because it's useful in security. Now there are these things called CNNs. Do you know? Do you know? And I'm like, of course I know. It's 2018, okay? And they were saying, tracking. Actually, not just looking at an individual frame. If you've got video, you can track the same identified objects across frames. Yeah, of course you can. But you can get the direction that things are moving in. Yeah, of course you can. Okay? You can make applications like this. You can draw a line or a perimeter, and you can count things in and out. And especially if you've got the direction as well, you can say how many people have gone from this lane to that lane, and maybe you even classify them and say how many cars took this way in and out of the intersection versus bikes. Yeah, of course you can. Okay? The one biggest advance was where at the state of the art, we're like, oh great, we've got NVIDIA GPUs. Now everyone lay into NVIDIA to go more and more powerful, more and more cores. Okay, not just cores for linear algebra that you used to do, give us tensor cores that directly have these operations. Out in the industry, nobody's buying a high-end NVIDIA card for each of their 1,000 cameras that they have installed in a city. Okay? So the actual advance was, okay, now we've got a low-power ARM chip that has some of those vector operations. Okay? There is a reason that NVIDIA wanted to buy ARM from SoftBank, which is it's not all about the H100s. Inference is actually about small, low-power edge devices. Okay? And that's what a security camera is. There's my 45 minutes. I'm already in the second half. Okay, so I get into the industry. They're very impressed by very basic things, but at least they're looking at edge. They're looking at acceleration in low-power devices. So I start to build a research group. I'll tell you more about this on Thursday, with academics. I hire a professor at a good computer vision group. We start hiring engineers, scientists, PhD students, and obviously what we start to talk about is things like segmentation. Bounding boxes were good when they were good, but actually, instead of having this very coarse outline of different kinds of objects, if we segment the scene, or here if we do synoptic segmentation, we really say, what class is every pixel? So we can look at pixel level boundaries, and we can understand better the relationships of things in space. This is more current. If we look at pose estimation, a person's not a box. If we understand their articulation, where their limbs are, especially in video as they're moving, then you can start to distinguish things like a handshake versus fighting. Okay? If you've got two bounding boxes for people and they overlap, heaven only knows what they're doing. But if you see whether they're doing this or whether they're doing that, you can start to do behavioral classification and then into behavioral prediction. So we're looking for ways to apply more recent things from the state of the art. And I will just give you a few examples. One of them is anomaly detection. If you understand better what's happening in the world and then something happens that doesn't normally happen, I don't know why we put bounding boxes on this one. I think just to illustrate what was involved in this. But the point is, we're not just counting things into the intersection, we're saying, why did this happen? Okay, and it happened because the truck turned too early. Okay, that is really useful for traffic managers to know that. Okay, not to wait for five minutes, if it's worst, for the dispatcher to say there has been an accident, and then rewind back their video for 5 minutes to see what happened, even though the vehicles have moved since. Better on the spot if we say, yep, no, there was an anomaly here, you need to look at this, okay? Now, in traffic, I was talking about this yesterday, I forget with whom, we often have what we call PTZ cameras, pan, tilt, zoom cameras, okay? So the traffic manager has a joystick and he can go look, that's where it happened, I need to look closely at that. Good if he's doing it live. If he's not doing it live, if he's looking at the recorded video, when we simulate it, you get this. You can't see those cars very well, you've got fixed resolution on the camera, you've got all sorts of noise due to, blur because of the move of the way that cars are moving, noise because of their light conditions. But given that we know those cameras, we can do a fairly good job at super resolution, okay? At recovering detail, given that we know what kinds of problems the cameras are prone to. So anomaly detection, super resolution, working with multispectral images. Let me tell you, here's a thought, I should have videos of this. The videos are real fun, but some of them I shouldn't show. The point is, in Aalborg, in front of the university, like a lot of Denmark, it's waterfront. You have a beautiful harbor in front of the university. And students being students, they love to drink in front of the university. And the bad thing about the water out there, I don't need to tell you in Estonia, it's damn cold in winter. If you get a bit drunk and stumble in or fall off your bike, you've got to be rescued quickly, okay? So for two reasons, Aalborg bought thermal cameras, okay? Runs in infrared spectrum. One reason is privacy, okay? You've got an RGB camera in a public space, people start to worry, what are you doing with that data? The other reason is there's a hot body, so hopefully it has higher contrast in a cold background and the cold water. I'll tell you a few things about that. They used Hikvision cameras. So we came along and said, our sister company under Canon makes very nice PTZ thermal cameras, please, can you get rid of those Chinese ones? And then lots of Kommune in Denmark said, yeah, we should get rid of them too. Another thing about this is people falling in happens very rarely. You will find this a lot in machine learning. You think, if I could diagnose that thing, it'd be $1 million idea. Okay? It's $1 million idea because it's costly but seldom happens. So how are you actually going to train a machine learning model against a massively biased data set? Then you start to look at synthetic data, for instance. Okay? So I have some nice videos that I'm not going to show you, please.
Pay the students to jump in.
Thank you. There are 3 stages to what we did. In this, so this was work that we did with Aalborg University and with the commune. This was thought 1. Okay? Get the students to jump in. They cannot fall into the water naturally. If you want to do fall detection, so we're not saying the bounding box is over the edge, we're saying, can we at least tell someone has fallen in? And better, can we predict if somebody's going to fall in? Okay? Because it's the person teetering on the edge or the person cycling like this, which is the danger that you want to tell ahead of time. Students cannot drop into the water naturally. They all did swan dives, and we said, yeah, no, thank you for getting in the water like you do all summer, but training against that isn't great. So then we got a dummy, a human-like dummy, okay? And this is the video. I should have these videos. Ask me and I'll show you. Maybe I'll show you on Thursday, but it's not warm. So you throw the dummy in and it flails around. That's a lot like falling in drunk, but the contrast isn't there. So then you put essentially a hot water bottle inside the dummy. You fill it with boiling water. It's nice and warm here, which is fairly realistic. And then you drop it and you throw it. It's very difficult to make much data because if you throw this dummy with a hot water bottle into the cold water in Aalborg and drag it out, which is the video that I've got, you have to put a whole lot of hot water in before you can do another case. So try grabbing 1,000 sequences of that. You're boiling a lot of hot water and throwing a lot of dummies. That's when we came around to what can we do with synthetic data. Okay, so we really built this semi-synthetic. We have this really nice public data set. You can look up at CVPR, the data set description that we collected. And it's really nice because we collected it for an entire year. So there's night and day, there's snow and rain and bright, there's different ambient temperatures, all in this infrared spectrum. You can download it. And what we did then, this is a little bit dummy looking, but we really took Unreal Engine and animated people doing these things against the real background. Okay? What we found with Unreal Engine, and incidentally, this is what NVIDIA do now, Omniverse says you can use the Unreal Engine, which is great at generating photorealistic things. We're proud Danes, so we started with Unity and then realized Unreal is better at photorealism. You're nodding your head. But then we realized games lie. Okay? Games have this beautiful physics engine, it has this beautiful rendering in visible light, but when you say in your game, now put on your infrared headset, it just turns everything green. It doesn't really reflect what happens in the infrared spectrum, which is, so one really easy way to see it, I'll show you some more pictures. If you wear a backpack, then the backpack has, and students do a lot, the backpack and your clothes have a really high contrast. Okay? So in infrared spectrum, it looks like, if you've got a dark backpack and light clothes, it looks like your backpack is really warm and your body is really cold. Absolutely wrong. Okay? Even without a backpack, you look at me and yeah, dark hair, light shirt, dark trousers. Absolutely not what my heat signature looks like. My heat signature says here, and here you're very hot, and here you're very cold, especially walking around. If you're good in Denmark, you'll have some warm boots on, but the visible light spectrum is not a good predictor for the infrared spectrum. So we trained this thing called thermal synth that said, okay, let's take the 3D models and the RGB images and turn the people into something that's more realistic in terms of heat, And we did the evaluation against the real captured video and said, yeah, this improves precision, blah, blah, blah. Super good questions, okay? So I was starting with the game engine. The fact that if you place things yourself, if you buy a bunch of Blender models and put them into Unreal, then you can make all kinds of situations. But then we get into actually a good use of Gen AI is to manipulate these, okay? You're not getting the stereotypes, you're not getting the weirdness because you have made the 3D model, but you are getting things that it's good at, like swapping faces. Okay, I'll tell you a little bit about that, about changing heat signatures. And for us, a big one is changing license plates. That also relates to privacy. Okay, break for questions.
One way to get around, I would not say around, but to get it in compliance with the EU AI Act and GDPR, would be to use the thermal camera. Is that because of the person is unidentifiable in the thermal camera? Okay. Are there any other methods, tricks that you can use? Because it's for many business use cases, it's like a killer.
I promise you, it's my very last slide.
Okay.
Although I just let it slip a little bit by talking about using Gen AI to substitute things. But honestly, that's my last slide, and then we can have that conversation.
And also, many people think that when you have this processing taking on board on the edge device, that it only gives out like, let's say 0 or 1. Has somebody fallen into the water or not, that this is like safe with the GDPR. So I would very much wait for your comments on that also. Thank you.
So again, oh yeah, you had the microphone. So two things. One, what do you do at the edge? What do you centralize? I saw a couple of posters about federated learning yesterday. That is really relevant. Second, it's not just binary. We work in the academic world, we talk about confidence because that's a good measure. In the real world, we talk about when are we intervening? When are we going to tell people to do something? And that's the third part of my talk. So you set up a lot really nicely, so much so that I want to say nobody's allowed to ask any more questions right now because this segues to the last bit of my talk, and then we'll have some questions at the end. 10:36, I finish at 11, right? Perfect. Good. So, it wouldn't be a talk this year if we didn't start talking about large language models. I think I don't need to tell you that I do what Isabel does. I ask it about myself. A lot like Isabel's, it's pretty good, but it does say, as my introduction said, that I am a VP of research. I'm not since April. Okay? I've got a different job title. Gemini doesn't know about it yet. Why doesn't it know? Why did I go to Gemini? Well, I went to Gemini because we are not just doing the set of tokens to a set of tokens. We're actually taking advantage of language embeddings in order to have source documents, which are close enough to what I'm asking that you can use that retrieval to augment the generation. And you probably know this RAG term for doing that. Okay? But it still doesn't answer my question. Okay, so it's been to my Google Scholar profile. I did used to be an academic. I do have a Scholar profile. You can go and look up my citations and H-index, which sadly are quite static in recent years. It also knows that I'm in industry, so it went to Sicherheit and found out I got made VP. Fantastic. Okay, but something went wrong here. Did I put it on the slide? Well, I had a conversation with it. Oh yeah, because it said I do computer vision, and I wasn't happy with that. So I said, not all AI is computer vision. What else has this fellow done? And it says knowledge graphs and semantic web services, blah, blah, blah. Oh, I didn't put it on, damn. Okay, so the reason it doesn't know that I'm fellow yet is I didn't put it on my Google Scholar page. I completely forgot. Okay, so it says, my Google Scholar says Barry Norton, who used to work at all of these different places, now he works at Milestone as a VP. Turns out that is the best evidence it could find. Unlike when I made VP, nobody's written a story in the industry about it, partly because they don't understand what my new job title is as fellow. Enough about LLMs, they're boring. VLMs are the new kid in town. Okay? So just as we can tokenize language, some languages better than other, and get embeddings for them, and use those embeddings with feed forward and attention heads, and we can do next token generation and validate that against the rest of the web and then instruction tune it. What about video? Well, we can tokenize it. When I started my group in 18, it was 100% not clear if transformers were going to be useful for computer vision the way they had been shown to for language. Okay? We won the first round. CNNs, it was computer vision. It was the handwriting recognition. It was the AlexNet looking at all of those classified images. Computer vision said, we've got this. And the language people said, oh, we're happy with doing our parsing and our SVMs. And then they did recurrent neural networks. So taking temporal into account. LSTMs were great, and we sort of were working out how to use those in video rather than just images. But then, bam, attention is all you need. Transformers, amazing, just amazing capabilities. You know, BERT within 1 year, the GPT models catching up, and then everything taking off. We were at that point of just after attention is all you need. I set the group in 18, and we're like, how do we use this for computer vision? What does it mean to tokenize the way that you can tokenize language, and language being linear? What do we do? Well, a bit like convolutions, we worked out if you get your patches of image right, you can treat those as a stream of tokens. And then there's what do you train against as an objective. There are certain things in images. It turns out the video is easier. What should you train towards? Well, the next frame of video. So what I was saying before about anomaly detection, the best way to do anomaly detection is predict the next frame of video, get the next frame of video, see how far they are out. Okay? So just like next token prediction, next video frame turns out to be really useful. I'm going to gloss over some things and say there's various ways to build a VLM. Okay? You can take an LLM and continue training by putting tokens from vision. Even better, pairs of vision tokens and language tokens. Even better if you interleave them. Or you can say, forget continuing training, everything that Isabel was saying about checkpoints. You can fine-tune against those things. Or you can train right from the start with cross-attention between language and vision. It's still a little bit, VLM doesn't mean one thing. VLM means a lot of different things. So I'm going to tell you about one family of models that I'm excited about. So you take this intuition of, yeah, you can turn some images into tokens that have embeddings in this shared aligned space with language. So you can give a language prompt. What's this guy and what's he doing? Get an answer from one of my favorite VLMs, which is Nemotron. It is taken from Llama and then trained towards vision. Let's have a look at the answer that it produces and talk about very carefully. I'm going to call them all hallucinations, maybe. But are they intrinsic or extrinsic? Why am I struggling with that? Intrinsic or extrinsic? Thank you. Now, we judge that not just with respect to what Isabel called the contextual knowledge that we've given, especially in FewShot, or the truth in what's being scraped for the web, like, for instance, Wikipedia. We also judge that with respect to the images that are shown to this VLM. So, its text, I asked it for a description. It's really a description and a summary, like a, what can you see, and summarize it for me. And the summary includes, I've got a light beard. Now, I never present with a light beard, but if you look at that image, the second one that I showed, I'm weirdly in light and in shadow, Maybe that's where the idea of a beard there comes from. It also says I've got a striped tie. I don't present in a tie either. But if you look at that one, yeah, there's some sort of stripiness around there. And then there's the reasoning. I asked it to make a speculation, to do some reasoning. And it said, this guy's probably a lawyer or a consultant. I would make a lot more money if I were a lawyer or if I were management consultant. Is that hallucination? No, I don't think it is. Okay? It's that I gave it a limited amount of context, both in image and text, to make the speculation that I asked it to do. So what could I do? I could do some prompt engineering. I could give it a better text prompt together with those images. And here's the bit where I say, this guy's a fellow at this video company. What is he doing in these pictures? It regurgitates a little bit, which I don't care for. But then it says, this is likely what he does, and therefore likely what's going on in those pictures. He's probably presenting at a conference and in this formal setting with his jacket on, because I always take my jacket off when I present. Okay? It's done a much better job at both the recognition and the reasoning because I gave it a better prompt. What I was talking about 5 years ago in the industry was this bounding box stuff. I cared about behavior, but the detectors that I got were bounding boxes. So if you train a detector for one of my scientists going through the door and one of my engineers going through the door after him, right? I've got a door detector, I've got a people detector, and the door changed state, it opened. Genji, the scientist, came in. Matthias, the engineer, snuck in after him before the door closed and stole some equipment. That is a real issue in security called tailgating, okay? But what I also said is computer vision's fine, but actually we have this equipment. We really have the access control card and the cameras. You don't need to judge the door state, but you can do things like use a detector model each side of the door for tailgating, and you can use a world model to say, what is the effect when someone tailgates? That person has now access to a different part of the 3D space. Can we tell the security operator, have a look there now because this tailgating has happened? Okay, so actively using the world model with that. Okay, I need a drink of water, so I'm going to do it. I hope I'm not too loud in explaining another security situation, much more recently. Oh yeah, and I should explain, this thing with the door and the access control and the camera, I built this to go to conferences with. I took it to Las Vegas and gave this demo live, and it's heavy. And it takes a lot of taking apart and putting together. So I am sorry for not bringing it to Estonia, but you can watch this guy tell you about it. Here we have a mock-up of a typical system with an access control door, the rear of which is monitored by a camera. So if I unlock the door, then if we open the door without access control, immediately, of course, we get an alarm. On the other hand, if we use our access control card, then there's a limited amount of time to go through the door before we hear another alarm that the door is open too long. On the other hand, what we often hear from security staff is that, especially in some situations, people will validate for the door and then validate a second time to hold the door open and use, for instance, a box to hold the door open. This vision language model was not trained to recognize doors as the model before, and certainly not boxes. In fact, it's trained on general purpose images. In 2020, I had a European project with 3 European hospitals in Marseille, the teaching hospital in Amsterdam, and a hospital region of Piedmont in Italy. Really happy about this funding we got, where really we could go and do video analytics and interventions in a hospital environment. But remember I said 2020? I could not get into a hospital. We were not even allowed into a single one of these 3 willing hospitals to do this. So that's actually why I started working on synthetic data. I built a virtual hospital in the Unreal Engine and started training things there because I couldn't train in the hospitals. But we kept going with the project. The EU gave us a year's extension, and we're still talking about what we can do. And the hospital said, something strange has happened. We used to use video analytics, and our retail customers did this especially, so that face covering is a danger sign. You need to tell the operators, to tell the security guards, someone is coming in with a motorcycle helmet on, or a bandana around them. This is dangerous. And it turned into no, everybody's got to wear a mask, please. It is a dangerous sign that someone is not covering their face, okay? They also said to me, we've never experienced this before. People are coming into the clinics and into accident and emergency that was open in hospital, and they're trying to steal PPE and hand wash, and even vaccines were stolen from a hospital. They're like, we've never seen theft like this before in hospitals, but people are scared. And we used to tell our staff, when they take a trolley to the supply cupboard, there's a bunch of things that they want, so what did they do? They wedged the door open with a box. Before it used to be please don't do that, it's dangerous. And it turned into no, don't do that. They're going to come in, and the patients are going to come in and steal the stuff. Okay? Now, we had trained analytics for covering your face, and it was quite easy to adapt that. It's just cover less, you can still see the eyes, it's mostly blue or white. We can do mask detection, but we'd never done box detection. The old school way would be that I train one, okay? I'd train a box detector, and I would get thousands of boxes and try to see if it generalizes to them. Instead, I used that equipment to send just a single frame to a VLM, and it's just incredible, right? It straight away gets there's a door with the hinges and a lock. At the end, the inference is it captures a moment that could be related to securing doors against unauthorized access. I didn't tell it any of that, right? I just gave it this image. Second paragraph, it does something pretty funny. It says, it reads the box and says, "Skab med omtanke," which translates to built with care in Danish. Yes, you read it correctly and you translated it, but then it says it's Danish and it's a box, so it must come from IKEA. No, that's a Swedish company, thank you very much. So incredible visual stuff, but it digresses into weird directions that I didn't want it to do, and that makes it more likely to make reasoning that I don't want, or inferences that I don't want it to do. So I would like to focus it a little more on the things that I care about, but, first try, 0 shot, really great, okay? I also promised yesterday that I was going to talk a bit about agentic AI, because we're not just doing, let's build a data set, let's do some training, let's have a look at the holdback. Oh, great, we've got a figure, now we can go send a paper to CVPR, NeurIPS. No, we're actually trying to make an intervention in the real world through security. So a sensible way to look at that now with generative models is to look at agentic AI. If you compare what we used to do, which is I don't want to labor this, but an alarm goes off in our system, we've interrupted the operator, they have to decide what to do. Do they respond to the alarm? Do they close the alarm? If they close the alarm, can we ask them, was it not right? And in the system as it was, they get this text box, okay? And most of them just leave it blank. They're not interested in documenting, was this right, was this wrong, was there something that you were more interested in, because it just gets saved into a database. The only ones who fill out that box using our software are Securitas, because Securitas contract for other people. So they have SOPs that say, we're running the cameras around here and the locks around here, and we're sending guards. So when we cancel an alarm on your estate, let's say the university, we need to say why it was cancelled. So if you come back on Monday and say, some of our equipment's meeting, we can validate that, we can prove through an audit trail we had done the right thing in running your security. What we thought was, what if instead of the reasoning and the learning being just in the mind of the operator, what if we rather follow an agentic approach that means that, so here is Alex at my office door holding it open and putting a box in my door. That's one of my 2 office doors. That's the one that I go out to vape, so I often let that alarm go off as well while I'm vaping outside. Alex's solution was to put a box in. An alarm was raised because the door was open too long. Now the operator looks at what happened, how should I respond to that alarm, and what we want to do, instead of giving them an empty box, is give them a little prompt that says, here's the image, what actually happened here, so that you can say, yeah, the box was left in the door, and then we do a bit of image segmentation to say, is this the box? Do we have it right? Yes. What do you want to do if the box is there? Do you want to suppress the alarm because that doesn't matter? Or do you want to raise a specific alarm to tell you when that happens? Okay? So you have low priority, the door's open too long. It happens. But you make a high priority alarm to say, someone's left a box in it again. Okay? And even further with agentic, so reasoning, the agent says, yes, I can see it. I can see that box. Learning, what should I do on your behalf as an agent in response to that? And the action can be that simple one, suppress an alarm, raise an alarm to higher priority, but using something like MCP, Model Context Protocol, there's all kinds of things we could do. We could actually query, okay, at that point in time that we see the card being used on the door, go to that system and say, give me the ID for the card that was used to open that door that then 5 seconds later got a box in it. Okay? Then go to the HR system and see who's registered against that card, and then go to the email agent to say, send that frame of video of the box to the email of that person on staff who used the card to commit that and say, do not do this again, or come and see HR, or come and see the security officer, right? In the agentic approach, let's give all of these things APIs, and let's let these actions from agents do everything, okay? Yeah, great, good idea, if you have a very solid model and a very solid set of human policies around what should you do here. Right, less than 5 minutes. I'm going to tell you about some techniques to improve the performance, and then I'm going to show you the last thing. We looked at off-the-shelf, zero-shot, did quite a good job, digressed into weird places. Before with the LLM, we did prompt engineering. You can steer this to some degree, okay? So the prompt engineering was, what is in this scene, or even more so, what I see in this scene is the box in the door, that's what I care about, and then use a generative model to say, yeah, I can see the box, I can see the door, I can see all of these other things, and I will be able to see them again now that you have, if you carry over this context between prompts, it can do that again. Yeah, previous interaction, now I'm getting into in-context learning, but previous prompt you can use to build a new prompt. In context learning, we can say, here are the examples before, yeah? Here is what you've seen and the prompt that I want as a response. What we can't do in our industry, or pretty much anybody's, unless you're Google, Meta, etc., or can raise as much money as Anthropic, is train a whole new model. So we have these well-known prompt engineering, few shot is interesting, because we're in the visual space as well as the language space. We have RAG, and we have fine-tuning. So 1 minute each. Few shot, you can say, here's a guy with a tie, here's a different guy, sorry, without a tie, here's a different guy without a tie, here is a guy with a tie, now tell me, describe this person, and hopefully you're not going to get me described as having a tie. In the industry application, you can say, this is a closed door, this is an open door, this is a box, and you will get a better, more focused response from the VLM around boxes and doors. RAG, you have textual information. This is classic RAG, like, for instance, job descriptions. So turn them all into embeddings, put them in a vector database. When you get your prompts, instead of going straight for completion, you match embeddings in the vector database, and you use those texts in the context in order to get a better answer. Okay? In security, what people started thinking it was all about was vector embeddings, embeddings in a vector database of image embeddings. So they were all thinking visual search. So you have seen scenes like this. I am interested in this thing visually. Tell me where they are by matching the vector. Actually, what I'm interested in, given that knowledge graphs and my background, is that particular thing called graph rag. Okay? So the non-industry example, classic example of a mathematical graph is an org chart. Who reports to whom? You can express that as a graph. Instead of a vector database, you can put it in a graph database. Now, you turn your prompts into embeddings. You use the embedding model generation to generate a graph query, okay? And the graph query retrieves context that can be used in generating a completion. In the industry, go back to my black thing that I built, a great graph, in general, is a world model. Here is a lecture theatre. Inside it, there's a lectern, there's a desk, there's these rows of seats. This is great to model with a graph. Okay? And the simple graph that I would talk about is there's a door, there's an access controller, and there's a camera, and they overlap. If I store that as explicit information, symbolic information in a knowledge graph, and I can retrieve that as part of my completion, then my completion can do things like, where was that scene? I've got the context for it. I've got it was captured behind this door, which is controlled by that access controller. None of that's part of the pre-training, okay? The weights, the parametric knowledge know nothing about my building and how I set up the equipment inside it, but I can represent that in, for instance, a graph, strongly recommend a graph, okay? And then I can retrieve that to add to the context to get a better generated output that includes both language and vision. Fine-tuning, you probably know this. One approach to fine-tuning is LoRa, freeze the weights, introduce some adapter layers, and all you've got to do is train the adapter layers. Very overview of parameter-efficient fine-tuning, but the point is you can do this to VLMs as well as LLMs. We are working with, okay, one little bit. You've got to do it responsibly. Even in context learning, I said, wow, we're going right back to the start. Even in context learning, I've got to use Windows to get back. I don't know why it jumped. There we go, there we go. I said, well, I didn't like that it put a tie on me. Oh, that's over, isn't it? Didn't like that it put a tie on me. I will give these couple of examples. I didn't mean to bias it, but actually what I did is showed it to men. It is much more likely now to tell me that a woman was giving a presentation at a tech conference. I biased it accidentally. If you're going to do fine-tuning, you need to give thousands of examples. There is the real risk of bias. There's also the risk that you're using video that you shouldn't be, that's privacy violating. This was license plates and the text on the van was removed. What's a good way to remove them? The last slide that I promised you is to use generative tech to swap out faces. This is a very subtle change on the right-hand side to my CEO, but facial recognition doesn't find him anymore after that change, and that is GDPR compliant. Okay? You have removed the personalization by doing this small generative trick in switching out license plates for license plates that don't exist and for faces to faces that don't exist. And we acquired this company, this startup in Berlin, who have good technology for this. So even though I've gone over, I have addressed 2 questions that came up in the meantime. That's my excuse. Thank you, everyone.